All right, hello everybody. Welcome back to data analysis. So today we are going to discuss maximum likelihood and hypothesis testing. The first part of this lecture is going to be on maximum likelihood, and we'll be introducing hypothesis testing in later chapters. I know many folks when they come to this class, they have heard the term maximum likelihood. They have some loose understanding of what it means, and we're going to shed some more light on the topic today. So as we get started, I just want to review the modeling assumptions that we have on our linear regression models. So we're assuming that y is, so this is a random variable y written in as capital here, and this is a row vector x. This is a random vector x and a coefficient vector beta and some epsilon term, right? And so we have these three tiered assumptions. The first one being epsilon means 0 for each x. Second one, epsilon means 0, constant variance. We also have this uncorrelated assumption. And then the third one, epsilon is normally distributed with mean 0, constant variance. This statement is independent of x. And then further, the epsilons are independent across the observations. Okay, so we go from uncorrelated epsilons across observations to independent. So throughout this lecture, we're going to be assuming assumption 3. Okay, so this is really important because we know we have these tools to do diagnostics to assess whether it's reasonable for us to assume assumption 3, right? So in the context of doing real-world modeling, you want to do your diagnostics, make sure that assumption 3 is reasonable before the conclusions of this lecture will hold. But for the purposes of getting us started and not having to do diagnostics each time in this discussion for the lecture, I'm not going to. But so just a caveat there. Okay, so let's talk about maximum likelihood generally. Okay, so I'm going to let F be what's called a parametric family of densities or mass functions. Okay, densities in the continuous case, mass functions in the discrete case. And so a parametric family is a collection of either densities or mass functions which depend on some parameter vector. Here I'm going to denote it theta. Okay, so it's a collection of densities, we'll just say densities for now, densities which are indexed by a parameter vector theta. Okay, so we'll denote by f of x given theta, some theta naught here. This is the PDF or the mass function which has parameter vector theta naught. Okay, the idea here, again, a parametric family, you give me a theta naught, then that value allows me to determine a density. Okay, so an easy example is normal densities, right? So normal densities, it's a parametric family which depends on a mean and variance term. Okay, so if you specify a mean and variance, well then I have these parameters. I can plug them into my parametric family, and I can get a density of a normal distribution. Okay. So this is some language here. So if I have a sample from n points, so I have sample of size n, and this sample is independent, okay, and identically distributed. You may have heard this in your intro stats course, but what we mean here, so independence is pretty clear. These random variables are independent. Identically distributed, meaning that these x's all have the same distribution. Okay, so I have this is referred to as a IID, independent, identically distributed. So if I have an IID sample from a parametric family with some theta value being selected, okay, then the maximum likelihood estimator for this value, this parameter value, maximizes the joint density of the sample as a function of the parameter vector. Okay, so like lots of things breaking down, but what I'm saying is that you give me a sample, and then the maximum likelihood estimate for this theta naught maximizes the joint density of the sample here. Okay. This is called a likelihood function. And it's actually the maximum likelihood estimator, again, so this is defined as the maximizer of the joint density, okay? And in general, so I've specialized this to the IID setting here as I've introduced it. It holds that the maximum likelihood estimator, even if maximizes the joint density, even when this sample is not independent, but that's a case we won't look at in this class. Okay, so let's put some equations on here because I think sometimes the equations are a little easier than all of the English. So we have an IID sample. So these are endpoints, independent and identically distributed, and they are drawn from some density, some parametric family for some value of theta. Okay. So the MLE, I put the hat on here to denote that it's an estimate. MLE is the maximum likelihood estimate. Maximizes the likelihood function, which is what I treat the joint density. I mentioned this on the previous slide, but just to drive the point home, this is the joint density of the sample x1 through xn, and this is as a function of theta. Okay, so because, well, we know, recall from your probability course that we can actually write a joint density. So if I have a joint density of a bunch of independent random variables, I can form their joint density by taking their product. Okay, so the joint density is the product of the densities for each of these random variables here. And their densities, because they're identically distributed, it's the same. Okay, so their densities are actually, they're all just this f of x given theta density. Okay, so so I've just simplified the likelihood here. And then in general, so the goal is we want to the maximum likelihood estimator, again, it maximizes this expression in theta. Okay, and so in general, maximizing this expression can be computationally difficult, and it's common to maximize the log likelihood instead. So instead of maximizing this, we maximize the log of this, right? We can do this because log is an increasing function. So the maximizer of this expression will maximize the log of this expression, okay? So let's work an example. So I'm going to consider a Poisson, these x's to be Poisson. Okay, so these n samples come from a Poisson density with parameter vector mu. This is our mean parameter in a Poisson random variable. Okay, and again, a Poisson family is a parametric family because you give me a parameter, this mean vector or this mean value, and I can give you a Poisson mass function. Okay, here this one is discrete, of course. Okay, so it's the mass function of a Poisson random variable. This is it, and so we can form the joint density for the sample of n sample of n points from a Poisson random variable or from a Poisson distribution as this product. Okay. And then the goal is, again, to maximize this quantity in mu. Mu is our parameter. So we want to treat this thing as a function of the parameter, which here is mu, and we want to maximize it. Okay. And we're treating, so it's typical. This is just hopefully drives this point home a little more clearly, but we typically treat densities or mass functions as functions of the x values, right? And what we're doing here is we're treating this input as data, right? We're receiving some sample, and then we want to maximize in mu. So we're sort of flipping that on its head. Instead of knowing a parameter and then caring about the density for the function for evaluation at x values. We have x values, we've realized data, and we want to maximize this joint density in the parameter value. And so we'll apply the trick that I mentioned on the last slide. The trick is, instead of maximizing this expression, we'll maximize the log of this expression, that is the log likelihood. Okay. So when we apply the log here, we can actually apply some tricks of the log, right? So remember, log distributes across products, and so distributes across products and becomes a sum. And so when we distribute the log across each one of these terms, right, we apply the log to the e to the negative mu. Log of e to the negative mu is just negative mu, and then so on and so forth. So we can distribute. We get this, bring the xi down from the log term, and similarly, this xi factorial is in the denominator. Okay. So this is the expression when we apply the log. This is the log likelihood term. And we see, so this will be easier to maximize for us. We can take the derivative and set it equal to 0. If we do this, right, if we take the derivative, well, this becomes negative 1. We have n of them. Okay. This term here, we get xi over mu, right? And that is this term here. And then I can solve and show that my maximum likelihood estimator for the mean of a IID Poisson sample is actually the sample mean. Okay. So what we've just shown is that the maximum likelihood estimator of this Poisson sample is its sample mean. So if you want to estimate this Poisson mean just given data, you would set up this log likelihood, and if you maximize it, you can show that the sample mean, we've just shown that the sample mean is the maximum likelihood estimator. Okay, so let's go back to linear regression, having talked about maximum likelihood generally. So again, we have this relationship between x and y, okay, and we're assuming this third assumption, right, that epsilon is normally distributed for each value of x. And we've shown this before, but we've shown that y is the mean of y is x beta, right? And the variance of y is sigma squared. This is for fixed values of x. Okay. So we have these two parameters here. So we have a parametric family for y, right? So y is distributed according to this parametric family. You give me beta, you give me sigma squared, and then I have a distribution for y, right? So let's estimate these parameters using maximum likelihood estimation, right? We can have a bunch of pairs of x and y. We can set up the likelihood, take the log of it, maximize it, estimate beta and sigma. Okay. And so here's a reminder: the normal density with mean mu and variance sigma squared. Its density looks like this. Okay. So if I have n samples, okay, sample of size n, let's say, the maximum likelihood estimator for these parameters, well, what I can do is just set up the log likelihood, or set up the likelihood here. This is the product of these normal densities. Okay, there's n of them. And maximize it in this b term, which is a dummy variable for my beta, and this sigma squared term. Okay. And so here I just want to emphasize this. So here we have the random variable minus its mean. And here we have the random variable y minus its mean. Okay, so this translation to plugging in the x's and y's in order to get the this joint distribution here, I should say. Again, we're just following the form, subtracting the mean from the random variable. Okay. All right, so we can do a couple of things. First, we have the sigma root 2 pi, this occurs n times. It doesn't depend on I. So we can pull all of that out of this product. Okay? And then we're going to consider the log likelihood instead. This is the trick that we've seen a few times now. And the idea is that this thing will be easier to maximize than the joint distribution here. Okay, so applying the log, again, the log distributes across all these product pieces, and then applying the log to the exponential, you just, the exponential and the log cancel, and you're just left with this negative quadratic term. Okay, so that's this piece. And then these two come from the sigma squared 2 pi term here. Okay. And so let's look at this. So I want to maximize this in B. The maximizer will be my beta hat MLE, my maximum likelihood estimator for the beta term. So if I want to maximize this quantity, or this whole quantity in B, well, this quantity doesn't matter to me, right? There's no b's in it. So maximizing this quantity is the same as maximizing this quantity in B, just considering the B for the moment. Okay. So, right, maximizing this quantity in B is maximizing this quantity. Okay. And actually, if we're just thinking again, just thinking about the B term, the maximum likelihood estimator for beta, maximizing this expression is equivalent to minimizing this expression. So what I've done here is I have said, okay, well, if I'm just choosing B here, well, then this 2 sigma squared is not relevant to me. It's positive. It's a variance. It better be positive. And instead of maximizing a negative, I can minimize its positive. And then if I'm going to I can just multiply positive constants and still end up with the same maximizer / minimizer if I'm considering this problem. I can put a 1 over n out front. The reason I could put a 1 over n out front, well, so it has the same maximizer, but why would I do that is because this should look very familiar to you. This is the empirical mean squared error, right? So by some manipulation, I've just sort of multiplied, divided by some constants, got rid of the negative. Maximizing this expression, which comes from this likelihood term, is equivalent to minimizing mean squared error. Okay, so this is a big deal. What we've shown is that the maximum likelihood estimator for beta minimizes mean squared error. Okay, so the least squares estimator is the maximum likelihood estimator for this beta term. This least squares estimator obviously minimizes mean squared error. So beta, and I just add again one caveat here. This is under assumption 3, this assumption about Gaussian noise. So we must have Gaussian noise. Assumption 3 here. Okay. So we must have the third assumption that gives us Gaussian noise and the independence that allows us to write a joint distribution as a product of univariate densities. And so yeah, then crunching through the algebra here, we've shown that maximizing this expression same as minimizing mean squared error. Okay. So what about the variance term? Okay. So the variance term is a little different, but sort of some of the same techniques. So we're going to maximize in this sigma squared. We can take a derivative with respect to sigma squared. This is interesting here. I'm going to treat sigma squared as its own variable, right? So you can just imagine instead of a sigma squared, I could just call this thing v, and then maximize in v instead of maximizing in sigma. Okay, this is just an algebra trick that makes my life easier. And I'm going to take the derivative with respect to sigma squared as if it was not as a variable, not as a function of sigma. Okay, I'm going to maximize in sigma squared, and I'm going to set it equal to 0. Okay, this is standard by now. If I do this, I get this log sigma squared, taking the derivative of this, I get 1 over sigma squared. That's this piece. Okay, just track through all my sigma squareds here. My sigma squared here becomes a sigma to the 4th. Okay, and again, this is because I am taking the derivative with respect to sigma squared, not sigma. Okay, but if I do this, I get sigma to the fourth here, set it equal to 0. This defines my maximum likelihood estimator, and this is what I get. Okay. And more algebra here. I'm going to multiply by sigma to the fourth on both sides. And I see here that adding over, dividing by n, my maximum likelihood estimate of the variance of epsilon is equal to, this is 1 over n. This is the mean squared error. Then this is for my MLE beta hat. Okay, so this again is a mean squared error. It pops out again. So this is our maximum likelihood estimate of our variance. Okay. So the mean squared error is come up two places. First, beta hat MLE, the maximum likelihood estimator of beta, minimizes empirical mean squared error, and the maximum likelihood estimator for sigma squared is the empirical mean squared error of this least squares estimator, beta hat. Okay, so double duty, but this is just working through some of this algebra. Okay, so here's a summary of our work. Okay, so what we've shown, this first part here is from previously, but the maximum likelihood estimator of the beta term is actually given by the least squares estimator, right? We showed that in this lecture, and then previously we showed that the least squares estimator has this expression, right? X transpose X inverse, X transpose Y, where X is our usual design matrix, right? The variance parameter, sigma squared, we showed it that just on the previous slides, we showed that the maximum likelihood estimator is the mean squared error of the least squares estimator. Okay, in matrix notation, that is this. This is mean squared error. So this is truth minus prediction, right? Take the dot product with itself, you get the sum of squares. Put the 1 over n out front for the mean. And then just following through this estimate for sigma squared, our maximum likelihood estimator for sigma is taking the square root of this mean squared error, that is the RMSE. Okay? It turns out, unfortunately, that the maximum likelihood estimator for sigma squared, this one here, is actually biased. Okay? What that remember what that means? That means that the expectation of our estimator is not equal to sigma squared. Okay? We can correct for this by altering the number of parameters in by altering what we divide by here. Okay? Let me just show this. So if we correct for the number of parameters in beta, we can make it unbiased. Okay? Doing so, we have the following. So instead of dividing by n, I divide by 1 over n minus p plus 1 here. So p plus 1, this is actually the number of parameters in beta. Right? Why is this? Because there's p predictors in x, and then one predictor, which is the intercept term. Beta 0, and then beta 1 through beta p. Okay? So it turns out, and we won't show it here, but this is unbiased for, this is an unbiased estimate of the variance term. Okay? And similarly, an unbiased estimate for the standard deviation, sigma, is a square root of this. Okay? So this is a correction which we can make so that this maximum likelihood estimator of sigma squared is unbiased. Okay? And notationally, I'm going to denote the maximum likelihood estimator with a hat on it. So hat on it is going to be maximum likelihood, and then the unbiased version is going to be denoted by S. Okay, so S squared, this is the unbiased version where I've corrected for the number of parameters in beta, and then the biased version is going to have a hat on it. Okay, so here's an example. So this is an example which we've seen in your intro stats course, but we'll review it given the knowledge we have now. So I have an IID sample from a normal distribution, mean mu, variance sigma squared. and I'm going to estimate mu and sigma squared using maximum likelihood estimation. Okay, this is actually a special case of our regression model, right, where we're just estimating a constant. We're estimating beta naught. Okay. Some calculus, I'm not going to run through this, but you can convince yourself of this case. Some calculus will show us that the maximum likelihood estimator of the mean parameter is the sample mean. Okay, that's nice. That actually matches what we had in the Poisson example, where the sample mean was our maximum likelihood estimator of the mean parameter. That won't always be the case, but it's nice when it is. And then applying what we talked about on the previous page. So we talked about the maximum likelihood estimator of the variance parameter is the mean squared error, right? So because this is just a special case of linear regression where we're just estimating a constant mu or our constant beta naught, we're just estimating the intercept term. We have biased and unbiased estimates for our variance. Okay, so on the top here we have the biased version, on the bottom we have the unbiased version. And what we've done here is we've corrected, right? Remember this expression is n minus p plus 1. Okay, well, we don't have any predictors, we just have an intercept term. Okay, so this is just n minus 1. So this is our unbiased version. This is the usual sample variance as you have seen it in your intro stats class, right? So the reason for this n minus 1 in the denominator is that it makes this sample variance unbiased for sigma squared in this setting. Okay. I want to make one other point clear. So I say that this situation can be viewed as a special case of our regression model where we're just estimating beta naught, right? So the idea here is x equals beta naught plus epsilon, where epsilon is mean 0 and normally distributed. Beta naught is some constant, right? So that is exactly matches what we have here. I can write, so xi, I could also write xi is mu plus epsilon. Epsilon is random, mu is a constant. I want to estimate mu, right? So this looks like our regression setting, and if epsilon is mean 0, so basically what I'm doing is subtracting off the mean from the distribution here, and I can break this into, I want to predict some random variable, estimating a constant piece, and I have some random noise, right? This setting where I estimate mu, it looks exactly like our linear regression case, and it is a rewrite of the estimation problem here for estimating mu, and then the estimate of sigma squared is an estimate of the variance of epsilon. Okay? All right. And so let's talk for a moment about an extension. We've talked about maximum likelihood estimation in the context of linear regression. We can talk for a moment about what's called Poisson regression. Okay? So the extension is as follows. So in linear regression, right, of course, when we have all of our assumptions, please don't forget this, we know that y, given some value of x, is distributed normally. This is what we've seen before. The mean is x beta. The variance is sigma squared. Okay. So what's happening here is that the mean of y given x is a linear function, right? You give me an x, the mean of y is a linear function in x. Okay. So what if instead we had y given x had a linear, its mean was a linear function, but instead of being normal, it was Poisson. Okay. So it's similar to what we've introduced in the sense that we have this linear relationship between the mean and the predictor variable. But instead of being normally distributed, I say, okay, what if it's Poisson? Okay. So y given x is a Poisson random variable now whose mean depends linearly on your predictors. Okay. This is called Poisson regression. And so if we have n samples, we can again estimate beta via maximum likelihood estimation. So we would maximize this joint distribution in B. Okay, so here I've written y is my Poisson random variable, xb is my mean. Okay, so if you were tracking what we had before in the Poisson mass function, we had e to the negative mu mu to the xi over xi factorial, right? And so what I've done here in writing this maximum likelihood estimation problem is I've replaced all the mu's, the means, with x beta, right? And xb, b being my dummy variable, and xi, my Poisson random variable, I'm replacing it with y, because y is now my Poisson random variable. Okay? So this is what we want to maximize for maximum likelihood estimation. Again, we will maximize the log instead. We can break this down into a couple of pieces. Once we apply the log and distribute across the product. In particular, this denominator piece actually doesn't matter at all because, for the sake of maximum likelihood estimation, because it does not depend on b. So we're maximizing this expression. This piece has no b in it. We can ignore it. So maximizing the log likelihood is maximizing this expression here. Okay. Unfortunately, we're not going to take a derivative and set it equal to 0 because this doesn't have a closed form solution, and instead you have to maximize this expression numerically. Okay. Thankfully, students in the operations research curriculum have to take optimization courses alongside their stats courses, so when you get to your nonlinear programming course, you will see some techniques to maximize this expression, but we're going to let R do it under the hood and not worry about the details of the optimization. But it is maximizing this log likelihood term. Okay, so that's Poisson regression. Another example is logistic regression. Okay, so logistic regression follows from, instead of saying that y given x is Poisson, what if y given x was Bernoulli? Okay, and again, the mean of the Bernoulli distribution will be a linear function of the predictors. Okay, remember Bernoulli is the distribution which is it's the mass function of flipping a single coin and counting how many heads you have, and the coin is allowed to be biased. So here, this parameter is telling us the probability of getting a heads. Okay. And so we can set up this problem, but unfortunately we have some issues. Okay, remember this parameter in a Bernoulli parameter. This tells us the probability of giving heads. It's actually a probability, right? So we might like to do something like this. This we say, well, we'd want the mean to depend linearly on the predictor. But unfortunately, we can't, right? So this is sort of the natural extension. But we can't do this, and the reason is that x beta, right? X beta is a linear function, and linear functions take values from negative infinity to infinity. But x beta in a Bernoulli distribution, the parameter in a Bernoulli distribution, is a probability, right? So we can't have it taking values less than 0 or more than 1. Okay, so this is not appropriate. So maybe what we could do is we could, instead of having the Bernoulli parameter depending on being x beta, we can take it to be maybe exponentiated x beta, right? And what we've done here is we've corrected the non-negativity, or corrected the negativity issue, because exponential will always make things positive, right? So this is close, but actually no cigar. The reason is that, right, again, the exponentiated linear function can take arbitrary large values. So even though we've corrected the negativity problem, exponentiated linear function can still be arbitrarily large, so it's not appropriate for modeling a probability. And so what we're going to do, the so-called the Goldilocks transformation that's going to work for us here, is we're going to take the Bernoulli parameter to be exponentiated x beta over 1 plus exponentiated x beta. Okay? And in general, you can probably look at this for a minute and convince yourself, but this value in here is between 0 and 1. Okay? So it will accurately model a probability, right? This is some positive number over 1 plus some positive number. It's definitely smaller than 1, and because they're both positive, it's greater than 0. Okay. So this will be our representation of the probability. This function f of x is, so this is kind of special, this exponentiation of x over 1 plus exponentiation of x, right? This sort of what we've wrapped this linear function in here is called, here I've called it the sigmoid function because it's the only sigmoid function we'll consider in this class, but in general it's a sigmoid function because there are other types of sigmoid functions. And the sigmoid function, what's important is that its shape is like this, okay? So the sigmoid function, what it does is it takes x values, which can be, arbitrary, and it maps them to be between 0 and 1. Okay, so this is the shape of the sigmoid function. So for large values of the, so as x beta gets very large, right? The mean parameter in the Bernoulli distribution will approach 1, right? So this would be x beta. X beta gets really large, the mean parameter approaches 1. As x beta gets very small, x beta approaches 0. Okay? So we're just wrapping our linear function in something that will allow us to interpret this as a probability. Okay? All right. And so let's actually set up the likelihood function given this representation. So remember the mass function of a Bernoulli random variable is this here. So this is the probability that this is x takes value 0 or 1. So if x is 0, then the probability that x is 0, well, we have p to the 0, this becomes 1. And we have 1 minus p to the 1 minus 0. So the probability that x is 0 is 1 minus p. And then the probability that x is 1, this one becomes 0, is just p. Okay. And so if we have a IID sample, okay, where y given x is Bernoulli distributed as where the mean parameter is the sigmoid function applied to a linear function, then the maximum likelihood estimation problem for the beta parameters is as follows, right? So this is p to the Bernoulli random variable times 1 minus p to the 1 minus Bernoulli random variable, and that matches the shape of our mass function here. Okay. And so we can do some algebra here. So this 1 minus p here, we can do some simplification. We can do 1 minus xib, turn this 1 into 1 plus x over 1 plus x, and do some cancellation, so just a little bit of algebra. And then maximizing the log likelihood instead of the likelihood here. Again, applying the log, distributing across the product, making them all sums. We maximize this expression here along the bottom. Okay. And so we can, if we stare at this long enough, do some algebra. This is my expression from the last slide. This is the log likelihood expression we'd like to maximize. We can simplify by canceling some of the 1 terms here associated with this log 1 plus x beta. Okay. And when we do so, we can simplify this expression to the following. Okay, so here we maximize this expression in B. Okay. So what we've done is, again, we've set up this joint distribution, maximize it in these x beta parameters, and reduced it to this expression. So again, we're not going to take the gradient, set it equal to 0. The reason is that this does not have a closed form solution for B or for beta hat, and so we're going to find we're going to maximize this expression numerically, and we're going to let R do the optimization, but this is the maximum likelihood estimation problem. Okay, so I hope you see the trend here. So the trend is, right, we assume some distribution or relationship between y and x. We set up we are able to come up with a joint density, and then we maximize that in this linear expression xb, which either captures the mean in the case of Poisson regression and linear regression, or it captures something very close to the mean in the case of logistic regression. We've applied this sigmoid function to be able to interpret it as a probability. Okay, so let's look at an example here. So logistic regression can actually be used for classification. So up until this point in this class, we've been only considering regression problems, and logistic regression, despite its having regression in the name, it can actually be used for classification. Okay, the reason is if I jump back to the what we're considering here, our outcomes here, our y's, are Bernoullis, and our Bernoullis take values 0 or 1. Right, so we can consider these 0 or 1 as two different classes. Right, you can call them whatever you want, but you have two different classes, and you want to distinguish between the two of them using a predictor x. Okay. So as an example, this is tongue-in-cheek, but as an example, let's predict if an individual has a math degree. Okay, I have a math degree, so I get to poke fun at this group of people. So we're gonna predict whether an individual has a math degree using their performance on a math test, measured as percentage correct, and their social skills, as assessed by their peers on a scale of 1 to 10, 10 being socially skilled, 1 being socially inept. Okay, so the joke is we would expect that these folks who have math degrees are going to score high on a math test, low on the social scale, but we're going to use these two as predictors. This is a contrived example, but we're going to use these two as predictors to decide this outcome of this y variable, which I've assigned 1, the outcome 1, that's the heads outcome in my Bernoulli random variable, to if the 1 is if the individual has a math degree, and 0 if the individual does not have a math degree. Okay, so I have two predictors, and then this y outcome. Okay. And so, again, so the idea for logistic regression is we have a fixed x1 and x2, and y given these x values is distributed Bernoulli, where we applied the sigmoid function to a linear function x beta. Okay? So we can actually write this as this linear function x beta. If we have two predictors and an intercept term, beta naught, then we can write this x beta term as, in more detail for this example, this is math test, social skills, intercept term. Okay. And then this is in vector notation, of course. So if I wrap these x variables into a design matrix along with a ones column, I have the following. Okay. And so the idea here is you're going to give me an x variable. Okay. You're going to give me a predictor. You're going to give me these predictors, right? You're going to come to me and say, all right, I've scored so well on a math test. I've scored, my social skills have such and such a ranking, and you're going to ask me to predict 0 or 1, right? Well, what I'm going to have is actually the output of this function. I'm going to be able to take my betas my beta hats that I've estimated, and I'm going to be able to say, okay, for this given x1 and x2, I can find this quantity, which is an estimate of the probability for that given x of being a 1, right? So if I can estimate the probability of belonging to class 1, I can guess whether or not this individual is a 0 or classified as a 0 or 1, right? If this value is large, this probability estimate, which I've called it p hat here. So p hat, I'm plugging in my estimate for beta and the predictor values that you've given me. If this is close to 1, this is p hat is close to 1, then the probability of belonging to being y equals 1, that's having a math degree, is high, right? And on the other hand, if this probability is low, then we're saying that the probability of being a 1 is low, i.e. we belong to the other class, which is, in this example, no math degrees. And so it's common to let p hat equal to 0.5 be your threshold. So p hat equal 0.5, that is, the probability of being a 1 is more than 0.5, then I'll classify it as 1. and if it's less than 0.5, then I'll classify as 0. Okay, so we're using this probability to decide whether the y value associated with the given x value is 1 or 0. So let's plot some data. So what I've done here is I've plotted a bunch of points, so I have a little bit of class imbalance. I have more not math degrees than math degrees. I've plotted exam scores on the x-axis, and I've plotted social skills on the y-axis. Okay, so again, this is from 1 to 10, and then the exam scores go from 0 to 100. And so we see that this plot here, the folks with math degrees, they tend to be larger on the exam scores and tend to be lower on the social skills. So we sort of have this region where most of the math degrees live. And notice that if I wanted to sort of draw a dividing line between these two classes, I couldn't do it perfectly, right? Some people score a little bit lower than we might expect on the exam, given that they have a math degree. Some people are more socially competent than we might expect from mathematicians, even though they have a math degree. Okay, so let me show you the outcome here. So this is if I plot the line where I'll show you how to do this in R in a moment, but I just want to talk about the high-level concepts. So if I estimate these beta coefficients, okay, as I've described on the previous slide, and then I plot the line where p hat, my estimate, is equal to 0.5, this is the line, this purple line, okay? So on one side of this line, I'm going to have all these points have p hat larger than 0.5, and on this side of the line, all these observations have p hat less than 0.5. So for these observations which have p hat larger than 0.5, I'm going to classify them as 1, that is, it's likely that the individual has a math degree, and for less than 0.5, I'm going to classify them as 0, it's not likely that the individual has a math degree. So this is the split that I found through logistic regression. Okay, and we can see that it actually does to our eye, it does a pretty good job of dividing the classes. Of course, I can't do it perfectly. There's some folks without math degrees who have been classified as having math degrees, and some folks with math degrees who have been classified as not having. But this is what logistic regression is doing for me. It's creating a linear function which separates these classes. Okay, separates these points based on our estimate of their class. Okay, so let's do this in R. We're gonna do this example. I'm gonna show you how I generated the data, and then we're also gonna do a Poisson example. Okay, so in the Poisson example, we're gonna predict the total number of this is round stingrays caught in California during various years. So we're gonna use the year as the predictor, and we're gonna use the number of another fish, a rockfish, caught during that year as predictors. So basically, we want to use the number of rockfish and the year to count, or to come up with a Poisson regression model for the number of round stingrays caught each year. And so, why is this Poisson? Well, remember the support of a Poisson random variable, the values it takes are non-negative integers, right? So, round stingrays, you can't catch half a stingray. So because the support of a Poisson random variable matches the support of this example, where we can only catch stingrays in positive integers or non-negative integers, it's natural to apply a Poisson regression here. Okay. We're going to use, I'll show you how to do this in R, but we're going to use the GLM function to do this in R. This builds a generalized linear model, and it will give us access to Poisson regression and also logistic regression. Okay, so we're moving past the LM function into the GLM function, and in order to do both Poisson and logistic regression. Okay, so let's turn to R. So first I want to talk about the math example that I did. Okay. So what I'm going to do here is I'm going to set my seed. The reason I'm going to set the seed is so I can get the same. When I generate random numbers again, I'm going to get the same numbers. So I'm going to generate my x1 and my x2 samples. Okay, so this is x1 and x2, and then I'm going to define the sigmoid function. So the sigmoid function is a function, it's exp over 1 plus exp. Okay. And I'll just say I'll generate these x1 and x2 randomly, trying to be somewhat realistic so that the mean exam score, the mean score on the math test is 72, the mean social skills is 5 with some standard deviation around both of those. Okay. And then I have a probability vector. Okay. So what I'm going to do, I chose an intercept. This is just some arbitrary number which I chose, some beta 1 coefficient and some beta 2 coefficient, negative 0.8. Okay, and so this is some probabilities of belonging to a certain class. So I take the linear function, I feed it through the sigmoid function to get probabilities, and then I'm going to generate a Bernoulli sample according to those probabilities. Okay, so if I look at this y vector, y is a bunch of zeros and ones, right? And then the probs vector is a bunch of probabilities. I fed this linear function through this sigmoid, this linear function into the sigmoid function to get probabilities as outputs. Okay. All right. So that's how. So look, the reason I'm spending some extra time on this is it looks a little different how we generate data in this case. Okay. So let's plot what I have here. So here's the plot of the folks without math degrees. I can add the folks with math degrees as these red squares. This matches what we had in the slides. And then add a little legend so we can see the correct categories from one another. Okay, so now let's fit a logistic regression model. So I'm going to build a data frame which has the x1 variable, the x2 variable. So again, this is exam score, social skill, and then the outcome 0, 1, 1 if they have a math degree, 0 if they do not. Okay, so building a data frame, and then I'm going to build my logistic regression model, which is I'm going to use a generalized linear regression model, or generalized linear model function, GLM. The formula is exactly the same as we did in the linear regression case. And here I'm going to say family equals binomial. And this family equals binomial specifies logistic regression. Okay, as I mentioned, we can also do things like Poisson regression. So this family equals binomial will get us will get us logistic regression here. The data equals math_df, so that's exactly as we would do in using the LM function, right? And then let's look at the coefficients of this model. Let me actually print them. So here's my coefficients, and let's compare that to the numbers I used to generate the data. So when I generated the data, I had my intercept negative 17, beta 1 was 0.25, and beta 2 was negative 0.8. So what I have is, these are sort of in the right ballpark, right? So my estimates, my estimates using maximum likelihood and logistic regression, my intercept term is estimated to be negative 18 instead of the truth, which is negative 17, 0.28 instead of 0.25, and negative 1.09 instead of negative 0.8. Okay. So one other quirk about logistic regression is that if you run the predict function on a logistic regression model, it will actually return what's called the logits. The logits are the x beta values before you've applied the sigmoid function. So these will not actually be probabilities. So right, I'll show you this. So we can see that, for example, if I just run predict on this logistic regression model, so this is my predictions on the training data, and these are obviously not probabilities, right? They're negative, they're above, some of them are above 1, some of them are below 0. So in order to get probabilities, you have to add this extra argument to the predict function, which is type equals response. What that says is make the type of the prediction match the response variable, i.e. it's on the scale 0 to 1. So by default, predict will give you x beta. To get the probabilities, you can use type equals response, or you can just take these logits and feed them through the sigmoid function. They give you the same thing. Okay, and then let's set this cutoff. Okay, so what I've done is I've circled all the points which are above these, which have probability of being a 1 greater than or equal to 0.5. Okay, so that again matches what we have in the slide. Okay, and then so lastly, this p hat. There's just some algebra for solving giving your coefficients, solving for the line where p hat equals 0.5. I've just worked that algebra offline here and plotted it, but you can do that if you have interest. And then this p hat equals 0.5 legend value. So this is the distinguishing line which shows us so values which are on this side or observations which are on this side are classified as a 1. Their p hat value is greater than or equal to 0.5, and less than this line here. On this side of this line, they have p hat less than 0.5. Okay. All right, moving on. Let's do this Poisson example, which I promised, about predicting the number of fish caught per year. This is in California, and again, we're predicting the number of round stingrays caught using another fish, the number of rockfish, and also the year in which the observation was recorded. So here's the data. Again, I'll post this code to the course website, so you have access to it. But this is my website. This is marinerecreationalinfoprogram.csv. So reading in this code, I'm not going to spend too much time in looking at it. But what I did is I had to do some data wrangling to get this into a format in which it was usable. So this is just me looking at it, seeing that it was not the way I wanted it to be, and parsing it into a shape that I wanted it to be. In particular, omitting NAs, things like this, just common data cleaning things. And so let's look at this fish data frame. Summary of the fish data frame, which is after cleaning. What does it look like? So what it looks like is I have a year from 1981 to 2019. I have the number of rockfish caught that year. This is the genus of rockfish, so I guess rockfish includes multiple species. And then number of round stingrays caught. Okay, so we see that the rockfish, of course, is just much larger. Number of round stingrays caught is much smaller. The maximum of around 5,800, a minimum of 0 recorded round stingrays catches in a certain year. Okay. And so let's see here. So here's a plot of the number of stingrays caught on the y-axis, year on the x-axis. Okay. Doesn't seem like there's a strong relationship, but we can try including it as a predictor and see if it helps at all. The number of rockfish caught and the number of stingrays caught, I might say that this has a positive relationship. It's kind of hard because some of these values are much larger here. So I might look at this on something like a log scale, but as it is, I'm just going to use this as an example for doing Poisson regression. But it does seem that there's a positive relationship between the number of rockfish caught and number of stingrays caught. You might imagine that this relates to general ocean health, but yeah, I'm not sure. I'm no marine biologist, but what I like about this problem is that the response variable, the number of round stingrays caught, is a non-negative integer, and so it fits the Poisson regression setting. Okay. And so here we're going to build the Poisson regression model. So Poisson regression model using GLM is exactly as before. So my response variable is round stingray. Okay. I'm going to use the rockfish genus as a predictor, and then here I have incorporated a little bit of extra code so I can play with this. But what I'm actually going to use is a polynomial predictor of the year variable. So this is just degree 1. So right now this is just the same as adding year on its own. but I've built this code here so I can play around and say, okay, what happens if I use a second degree polynomial in year? Does it help me? Okay, so I'll just leave it as it is. So this is round stingray as a function of rockfish genus and year. In GLM, I'm going to do family equals Poisson. Okay, that allows me to, that does Poisson regression for me, and again, I specify my data just like in the LM model. Okay. Here's my coefficients of my Poisson regression model. I have my intercept, I have the rockfish genus coefficient, and then I have the year coefficient. Okay. Again, I can come up with my predictions. Here I will use type equals response. That'll give me my predictions on the same scale as the response variable, so I can compare them to directly to my response variable. So for example, our prediction here is given the year, given the number of rockfish caught, we predict 786.5 stingrays in that for that observation. Okay. We can extract residuals exactly as we did before. This is the truth minus the prediction. Okay. We can do things like compute training root mean squared error, right? Training root mean squared error we can compute just as a square root of the mean of the residuals, right? So this is exactly as we've done before. Here we have to just include this additional argument for the prediction function. Okay, predict or resid function. So here we're using resid. I can compare this Poisson regression model to a straight linear model. So in a linear model, we're not using this Poisson distribution. We're using we're assuming that epsilon is normally distributed if we have this third assumption. So we're estimating using the least squares estimator instead of maximum likelihood estimator in a Poisson model. The mean squared error of that model is very, very similar. So this is the least squares estimator. This is the Poisson regression model. It's very similar. The advantage of using a Poisson regression model here is, as we said, the support more accurately reflects the random variable that we're actually receiving, right? The x values, we know that they must be non-negative integers, and so the Poisson regression is measuring that. We also have that the least squares error, the root mean squared error is smaller in the Poisson regression model, very, very slightly so. So not sure that it's making a huge difference, but this is just a comparison of the two of them. Okay, so that is what I have to say about Poisson regression. Let me just summarize some quick takeaways here for logistic and Poisson regression before we take a break and before going on to the second part of this lecture. And so the summaries are, as we've talked about, so if y given x belongs to a parametric family, okay? So parametric family, which we've talked about normal distributions, we've talked about Poisson distributions, we've talked about Bernoulli distributions, and those corresponding to your standard least squares estimator, your Poisson regression, or logistic regression. Then we can estimate the parameters in that parametric family as a linear function of x, right? The one that was tricky for us was this logistic regression where we had to first feed it through a sigmoid function, but we can estimate those parameters using maximum likelihood estimation, right? Forming a joint density, maximizing it as a function of the parameter, and the computational trick is usually it's easier to maximize the log likelihood than the actual likelihood itself. Okay, so these models that I've just described, they're called generalized linear models. Okay, there are some extra restrictions on what it means to be a generalized linear model, which I'm not going to talk about here because they're a little mathematical, but in general, this theme of you're estimating the parameters in a parametric family using a linear function of a predictor, this is generalized linear models. We've talked about Poisson and logistic regression. We've talked about how logistic regression is our first tool in this class that we can actually do classification with. You're going to spend a lot of time talking about generalized linear models in your advanced data analysis course, the course that comes after this one. But I want to mention them here if only to sort of get you thinking about them, and because it's very natural to introduce them in the context of maximum likelihood estimation as we have here. Okay, so that's all for now. I will see everybody next time.